Okay, for part C, we were just about to get into what are known as ionic type compounds. Ionic type compounds are compounds that involve ions, hence the name. And it's the ionization of the atoms that actually causes them to be attracted to each other. And that attraction is what's known as an ionic bond. So essentially, the way you can recognize an ionic compound is that it will involve metals and non-metal or a polyatomic ion. So it's important to have familiarity with the layout of the periodic table so that you can recognize which elements are metals and which ones are non-metals and hydrogen. And if you see a metal and a non-metal together, that means that that's an ionic compound, like sodium chloride, NaCl, metal, non-metal. That's an ionic compound. Calcium oxide, CaO, metal, non-metal. That's an ionic compound. I'm trying to think of something else. Lithium carbide. Lithium carbide, metal, non-metal, lithium carbon. That's an ionic compound. Okay. And the other thing that could be involved would be polyatomic ions. Anything that has a polyatomic ion in it is an ionic compound. It's important to learn to recognize the formulas for the polyatomic ions, because the formulas of a compound with a polyatomic ion in it will not always make it obvious that there's a polyatomic ion in it. Like, for instance, sodium nitrate, which has the formula NaNO3. It just kind of runs right in together, but you can see there's a metal there, and there are two different nonmetals there. So this is metal and nonmetal. That makes it an ionic compound right there. Also, you've got the nitrate polyatomic ion involved, which that right there makes it an ionic type compound. It's possible to have a compound made up of two polyatomic ions, which would not involve any metals at all, and that would be ionic also, like ammonium nitrate. So, or sorry, no. Ammonium chloride actually is what I was writing. That's an ionic compound too, but NH4NO3. And that's the way it would normally be written. Ammonium is a polyatomic ion, and so is nitrate. So two polyatomic ions together, that's also an ionic type compound. Even if it only involves one polyatomic ion, it's still an ionic compound, like, say, ammonium chloride, NH4Cl. Again, no metals anywhere in that formula. Nitrogen, hydrogen, chlorine, those are all non-metals. But the fact that you've got the ammonium ion involved in the formula, that makes it an ionic compound. And it's important to recognize which compounds are ionic and which ones are not, because for one thing, that tells you a lot about the properties of the compound. And it also tells you a lot about whether it's likely to be soluble in water or not. And it also tells you how to name it, because there are different rules for naming ionic compounds versus compounds that are not ionic, which we're going to see in a little while. And essentially, going back to the beginning, what happens is that you'll have a metal, or a positive ion anyway, that transfers an electron or more than one electron to a nonmetal, and the metal becomes a positive ion, and the nonmetal gains electrons and becomes a negative ion. Positive and negative charges are attracted to each other, and that attraction is what's known as an ionic bond. And you have the beginnings of an ionic compound. So for instance, sodium chloride, sodium, and you can write this with a little zero charge above it if you want to, just to emphasize that we're talking about the element sodium. And will give up one electron and become sodium plus ions. Chlorine, the element with zero charge on it, really wants to take in one electron. So if there's a chlorine nearby, it will very eagerly take in that same electron from the sodium and become chloride ion, or Cl minus. And now the Na plus and the Cl minus are attracted to each other, and you get NaCl. If you have, say, magnesium in the presence of chlorine, the magnesium will give up 2 electrons to form Mg+2 ions. And that's, again, because magnesium is in group 2. And also because magnesium needs to lose 2 electrons to get to the same number of electrons as the previous noble gas. And say if chlorine is nearby, each chlorine can only take in 1 electron to become Cl minus, because once it does that, it has the same number of electrons as argon, which is a noble gas, which makes it stable. So each chlorine only wants to take in 1 electron. But if you've got chlorines around, there's probably more than one, so a second chlorine can take in the other electron from magnesium, and that becomes Cl minus also. And then the Mg+2 and the 2 Cl minuses are attracted to each other, and they clamp together and form MgCl2. And that is an ionic compound. For some of the properties of ionic compounds, they are all solids at room temperature. They have very high melting points and very, very high boiling points. The high melting point, for example, sodium chloride, which is certainly the best known ionic compound, has a melting point of 801 degrees Celsius, which sounds pretty high, but remember that's Celsius. To put it into terms that you're probably more familiar with, look at the Fahrenheit temperature. 1473 degrees Fahrenheit just to turn it to a liquid. Okay. And then to boil it, you need 1413 Celsius or 2669 Fahrenheit. So yeah, those are really, really high melting points and boiling points. And other ionic compounds are similar. They are all solids. They tend to be brittle. So if you take a big chunk of rock salt, like you put on the roads in the wintertime, and hit it with a hammer, you're going to get a whole bunch of little bitty pieces of rock salt, rather than a flat pancake of salt. So it doesn't squash out, it'll just shatter. The solids are mostly white in color. There are some exceptions, especially when you get into some of the compounds that involve some of the transition elements, like copper and iron and nickel and cobalt and things like that. Some of those have colors, but most ionic compounds end up being white or off-white. They are crystalline, which just means that they really exist as a 3-dimensional array of alternating positive and negative ions. And I mentioned that once before when I was going over empirical formulas, and I don't know if I can find where I drew it out or not. I'm not finding it. You can look back and find that, where I drew the lattice of sodium chloride. The thing is that the attraction of positive and negative ions doesn't just go in one direction. This sodium ion is going to be attracted to one chloride ion in each direction. So it's going to be attracted to a chloride ion to the right and to the left and above and below and in front and behind. And that's going to go on and on and on in 3 dimensions. And so the formula that we end up with overall is essentially the empirical formula for the overall structure. Or you can just also come up with the formula from looking at the charges on the ions and putting them together in the lowest whole number ratio that will give you 0 charge overall. So Na plus and Cl minus, obviously, if you put them together 1 to 1, they cancel each other out and you get 0 charge overall. If you have magnesium chloride, you can count up the number of magnesium ions and the number of chloride ions in the 3-dimensional array, and you'll always end up having twice as many chloride ions as magnesium ions. So the formula is MgCl2, or you can just look at the charges. Mg+2 takes 2 negative 1s to cancel it out, and so it's MgCl2. Pretty simple overall. But that's what we mean by crystalline. There's a regular repeating pattern of the arrangement of the ions in 3 dimensions. The ions are not just thrown in together in any old order at random. They are poor conductors of electricity as solids, but if you melt them or dissolve them in water, they are good conductors of electricity. Because what happens is if you melt them, that frees up the electrically charged ions to move around, and those electrically charged ions can convey an electric current. Okay, so either as molten liquid or dissolved in water, they conduct, ionic compounds conduct electricity quite well. So as I was saying, for the formula for the compound, the overall charge of the ions has to cancel out. So you need the same total positive charge as total negative charge, so there's no charge overall. And that's true for large samples and for the formula unit, or the formula that we use for the compound, the empirical formula. So coming up with the formulas of ionic compounds, essentially it's what I mentioned just a moment ago, the lowest whole number ratio of the cations to anions that will result in 0 charge overall. And it works the same way for monatomic ions, that is the simple ions derived from one atom, as it does for the polyatomic ions, either way. Just remember, for the polyatomic ion, the charge applies to the whole ion collectively. So if we have a sulfate ion, the formula is SO4, with the charge usually written as a superscript after the formula as 2-. That 2- belongs to the entire unit of SO4, not to any one atom in the SO4. You can also write it, if you like, as SO4 with parentheses around it, with the -2 outside the parentheses, which kind of emphasizes the fact that that charge applies to the entire thing collectively. Okay. Okay, and that's what I was saying about the 3D array there. So for the formula for an ionic compound, again, it's the lowest whole number ratio of cations to anions that will give 0 overall charge. It's also the empirical formula that you get if you actually counted up the numbers of positive and negative charges in a sample of the substance. The cation is always written first, and the anion is always written last. That's kind of easy to remember because the cations are almost always metals, and the anions are formed from nonmetals. And so you just go left to right across the periodic table. The element on the left usually comes first, and the element on the right usually comes second, left to right. So for instance, like I said, NaCl, MgCl2, CaO, that kind of thing. And so some examples again, if you have Na plus and Cl minus, they will obviously go together in a 1-to-1 ratio and you get NaCl. If you have calcium plus 2, then obviously it's going to take 2 Cl minuses to cancel out that plus 2, and you're going to end up with CaCl2. You've got a total charge from the calcium of plus 2 and a total charge from the chlorides of -2. Plus 2 minus 2 gives you 0 overall. Same with polyatomic ions. If you have, say, Na plus and a sulfate ion, obviously it's going to take 2 +1s to cancel out the -2 on the sulfate ion. So you need 2 sodiums, Na plus and Na plus, that's a total plus charge of 2. And the sulfate ion gives you a total negative charge of 2. That's 0 overall. And we write the formula as Na2SO4, because it takes 2 sodium atoms to cancel out the charge on 1 sulfate ion. If you have, now a harder one, if you have calcium plus 2 ions with phosphate -3 ions, there's no common factor there. You basically just have to multiply them by each other. If you have 3 calcium plus 2s, that gives you a positive charge of +6 total. And if you have 2 -3s, that gives you a total negative charge of -6, and +6 and -6 will cancel each other out, and the overall formula ends up being Ca3PO4 2. Remember, this is what we do with a polyatomic ion when we have more than one of them in a formula. You put parentheses around the formula for the entire polyatomic ion, and then put the number of polyatomic ions you've got outside the formula, or outside the parentheses. It was the same with CaNO3 Essentially what CaNO3 means is you've got a calcium and a nitrogen with 3 oxygens on one side and a nitrogen with 3 oxygens on the other side. That's CaNO3. If you want to know how many total atoms you have, you look at the formula, you use the subscript for each element. And if it's a polyatomic ion and it's in parentheses with a subscript outside the parentheses, then the total number of atoms of each element would be the subscript inside the parentheses times the subscript outside the parentheses. So when we say we have CaNO3, that means calcium with 2 entire nitrate ions attached to it. So the number of nitrogen atoms would be 1. We don't know, the 1 is understood here. You don't normally write the 1, but 1 times 2. So there should be 2 nitrogen atoms in this compound, and sure enough, there are. For oxygen, it should be 3 times 2, or 6. And sure enough, 1, 2, 3, 4, 5, 6. So that's how you'd find out how many atoms there are in the compound. In calcium phosphate, each unit of the compound would have 3 calcium ions and 2 atoms of phosphorus and 8 oxygens. A useful shortcut on coming up with the formula for ionic compounds is cross-multiplying. And the idea in cross-multiplying is that the charge on one ion becomes the subscript on the other ion. And you just make sure you drop the signs, and vice versa. So if you have NaCl, you can reason it out and say, okay, +1, -1, 1-to-1 ratio. Fair enough. But you can just cross-multiply. The charge on the chloride is 1-, so 1 is the subscript for sodium. The charge on the sodium is 1+, so the subscript on the chloride is 1. Na1Cl1, that's NaCl. For calcium chloride, you've got calcium +2, so 2 becomes the subscript on the chlorine, and you've got Cl -1, so 1 becomes the subscript on the calcium, and you end up with CaCl2. With sodium sulfate, you've got Na+1, so 1 is the subscript for the sulfate ion, and the sulfate has a charge of -2, so 2 becomes the subscript for the sodium. Na2SO4 1, which is normally just written as Na2SO4. About the parentheses, normally we only use parentheses around the polyatomic ion if there's more than one of them in the formula. Normally, if there's only one polyatomic ion or one example of each polyatomic ion in the formula, we normally don't use parentheses around the polyatomic ion, but I'm not going to mark it wrong if you do. It might be useful, especially at first, if just looking things over, anytime you recognize a polyatomic ion, it's probably not a bad idea to put parentheses around it. Just so you kind of remind yourself, that's a polyatomic ion. It reacts as one unit. It probably stays together during its chemical reactions. And in naming, it gets one name. So that you'll remember to name this as sodium sulfate instead of sodium sulfur tetroxide or some weird thing like that, which is something I see a lot. Okay, so technically it's only correct without the parentheses, but you can use the parentheses around polyatomic ions if you want to, and I'm not going to get worried about it. This cross multiplication technique is especially useful when dealing with things like calcium phosphate up above there. Calcium has a charge of +2, phosphate has a charge of -3. You can figure out how to get the charges to be equal, but you can also just cross multiply. 2 is the charge on calcium, so it's the subscript for phosphate. 3 is the charge on phosphate, so it becomes the subscript on calcium. Ca3PO42. There you go. You do have to check though, because for one thing, remember, the formula for an ionic compound is almost always the empirical formula for the compound, the lowest whole number ratio of one element to the other. And cross-multiplying can occasionally lead you astray. Like, for example, with calcium oxide. Calcium ions have a charge of +2. Oxygen or oxide ions have a charge of -2. If you cross-multiply, you end up with Ca2O2, which does have an overall charge of 0, but that's not the lowest whole number ratio. These subscripts are both divisible by 2. So if you then do that, you get CaO, which is the correct answer. So you do, if you're going to cross-multiply, you have to remember as the final step, check to make sure that you've got the lowest whole number ratio. Because if you don't, it's not the right form, it's not the right formula. Okay, we'll get the naming ionic compounds in a little while, but first, going over some of the basic characteristics of molecular or covalently bonded compounds. These are often called covalent compounds, and just through sheer habit, that's the way I usually refer to them. So if I talk about covalent compounds, I really mean covalently bonded compounds, or in other words, molecular compounds. These compounds involve only nonmetals. And remember, there aren't very many nonmetals in the periodic table. Basically, these elements in the upper right-hand corner and hydrogen. That's it. So you might think, oh, well, there can't be very many of these types of compounds. Oh, but you would be wrong. There are many, many, many of them. It's kind of like saying, there are only 26 letters in the English alphabet, so there can't be that many words, can there? Well, yeah, actually, because there is practically an infinite number of ways that you can put those letters together, and there's really no limit into how many of those letters you can put together to form a word. And so, yeah, you can make a whole lot of words out of 26 letters, just as you can make a whole lot of compounds out of just these elements. So they involve only nonmetals. If you see a formula for a compound and all of the elements in that compound are nonmetals, and there are no polyatomic ions, then it is a covalent or molecular type compound. Among the nonmetals, the attraction for electrons is fairly similar from one element to another. So, oxygen has a pretty strong attraction for electrons, but so does fluorine, and so does nitrogen, and so does chlorine, and so does sulfur. So they're not all that different. And the result of that is that you can't get a situation with nonmetals where one element is actually going to take electrons away from another element. And they end up having to share the electrons instead. So covalent type compounds are all about sharing of electrons between nonmetal atoms. And they're sometimes called molecular compounds because they exist as independent, separate molecules, sort of independent of each other, not the 3D networks like you have for ionic compounds. So separate individual molecules. Some properties of molecular or covalent compounds is that, for one thing, they can be solids, liquids, or gases at room temperature. Some examples of covalent type compounds that are solids at room temperature would be sugars, like sucrose, table sugar, or glucose, the sugar that's in your blood. When they're pure, those are solids at room temperature. Also waxes, whether it's like car wax or candle wax. Those are examples of covalently bonded compounds. Liquids, water, for example. Water is a molecular or covalently bonded compound. Hydrogen and oxygen are both nonmetals. So H2O is definitely a covalently bonded compound. Alcohols like ethanol or methanol. Ethanol is the alcohol you can drink. Methanol is the alcohol that's in windshield washer fluid, which you definitely shouldn't drink. Isopropyl alcohol, which is rubbing alcohol. Those are all liquids, and they're all molecular or covalent type compounds because they involve carbon, hydrogen, and oxygen, and those are all nonmetals. Some of the examples that are gases at room temperature would be carbon dioxide. Carbon and oxygen are both nonmetals, and so they're covalently bonded to each other. And carbon dioxide consists of little separate units, each containing one carbon and two oxygens. So CO2, 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 not attached to each other though. And also CH4, methane, and also ethane and propane and butane. Compounds like that are covalently bonded, and they are gases at room temperature. For compounds like this, they have relatively low melting points and boiling points. Even the solids have relatively low melting points and boiling points. Obviously, if it's a liquid, then its melting point is below room temperature. And if it's a gas, then melting point and boiling point are both below room temperature. The solids can be brittle or malleable. And here's some examples up here. Sucrose is a sugar. Those molecules or those are fairly brittle. If you have a chunk of sugar and you hit it with a hammer, it's going to shatter into smaller chunks of sugar. But waxes, on the other hand, tend to be fairly flexible or poundable. If you take a candle and hit it with a hammer, it's going to squash out. And some parts might break off here and there, but most of it will just squash out. They are poor conductors of electricity in general, and it doesn't matter whether they're solid, liquid, or gas, or, well, I was going to say dissolved in water, but compounds like this generally don't dissolve in water very well. The formulas can vary for compounds involving the same elements. So as with the polyatomic ions, when you combine non-metal elements with each other, you can often do it in more than one way. Like, for instance, carbon monoxide versus carbon dioxide, CO versus CO2. You can do that. And those are two different compounds, but they involve the same elements. If you look at ionic compounds like sodium chloride, for instance, sodium and chlorine can only combine with each other in one ratio, NaCl, that's it. And that's the way it is for the other ionic compounds too. But for molecular or covalent type compounds, you can often have several different compounds involving the same elements in different ratios. Yeah, okay, so that's what I was just saying. The formula for the molecular or covalent compounds is not necessarily the lowest whole number ratio of the elements. Sometimes it is, sometimes it isn't. What the formula is whatever is present in each molecule of the substance. So in water, each molecule has one oxygen and two hydrogens, and so the formula is H2O. When writing the formulas for molecular type compounds, we also tend to go left to right on the periodic table. So hydrogen's here, oxygen's here, so the hydrogen comes first, usually. Hydrogen peroxide, on the other hand, has molecules, each of which has two oxygens and two hydrogens. So the formula for that is H2O2, even though the lowest whole number ratio would be HO. Okay, so for the covalent compounds, the ones involving nothing but nonmetals, we're looking at what each molecule actually has in it, not the lowest whole number ratio. All right, and I see I'm pretty much out of time here, so I guess that means that nomenclature will have to, that is naming the compounds, will have to wait until next time. So until then, I'll see you later.